Hello, in this video, we are going to learn how to do some problem solving using forces. And primarily, the approach we're going to use is the same that we have been using all year. We are going to picture the situation, represent the situation, then create the equations that we're going to use from the representations, and then we'll solve the equations. And I just want to emphasize that in this process, this part right here is the setting up the problem. And all of that can be done before you even bother to ask yourself, how do I solve this? Because once you have the equations out, it'll be much easier to figure out where to go in terms of your problem solving. All right, so let's get started by looking at a particular problem. So I have this problem here that I've created. Notice that I have this process up here. And because we're working in forces, our representation will be free body diagrams. Our equations we're going to create are called net force equations. And so let's get started. So we have a 30 kilogram sled full of logs being pulled from rest by a rope, which makes an angle to the ground. The snow exerts 15 newtons of friction on the sled, and the angled rope has the effect of exerting 60 newtons horizontally and 25 newtons vertically on the sled. And then we want to do three things: calculate the normal force, calculate the acceleration of the sled, and calculate the speed of the sled after 3 seconds of pulling. So first thing I want to do is to actually try to picture this situation. So I'm going to make myself a sled here. And then it's being pulled with some kind of rope like this. Maybe there's a person over here pulling it. Something like this. And they're going to be pulling it this way. They're going to start at point A. And it says it starts from rest. And I'm going to pull over. And at some point later, 3 seconds later, it looks like it's going to get to point B. So that's our little picture of what's happening. It's a picture of the story. And now we're going to represent the important quantities here. And I'm going to start by noticing that the first thing I want to do is calculate a force and then an acceleration. And those are good clues that we're looking to use some problem solving about forces. And so to do that, I'm going to draw a free body diagram. I think I'm going to draw my free body diagram up here to leave a little bit more room down here. So here is our sled. And we want to look at the objects that are interacting with the sled. And so one object is the rope, and we'll use the R as a subscript for that. A second object is the snow, and we'll use, or maybe we'll just use the ground because I don't want to get snow mixed up with sled. We'll use ground. And then a third thing interacting with the sled, of course, is the earth. These are all objects interacting with the sled. All right, so now let's go ahead and draw our free body diagram. That is all the interactions on the sled. So first interaction I notice is that there's a rope pulling up at an angle. That's going to be something like that. Let's call that tension, rope on sled. And then there's some friction, which I'm going to put right here. Friction, ground on sled. And then there is the weight of the sled, which is the earth pulling down on the sled. And then there's the normal force from the ground pushing up on the sled. Now you'll notice I made the ground, the normal force, a little bit less than the weight. And the reason for that is because I know the sled is not accelerating up and down, and therefore the net force up and down must be zero. And therefore I must include the weight being bigger than the normal force because there's also some upward pull from the rope. And the normal force and the rope upward pull, therefore, must balance the weight. So that's why I drew them like that. And none of these vectors can I draw the little slash marks because none of them are obviously equal. Now the next thing I want to do is set up my net force equations. After I picture and represent, now I'm going to create my equations. Now the net force equation is simply the way we take the relationship between acceleration, net force, and mass that we learned about in the last video, and then actually use that relationship. And the way we're going to build a net force equation, that's a term we're going to be using a lot, is we're going to look at our free body diagram, and like our pie charts and our graphs, we're going to build the equation from the free body diagram. So I'm going to look first at all of the vertical forces acting on the sled. I think maybe I'm going to put in the vertical force tension from the rope on the sled in the y direction or the vertical direction. I think I'll put that in there. And make my lines a little thinner so that it's easier to read. There's a similar force in the x direction. This isn't really a separate force. Tension rope on sled in the horizontal direction, which we're going to call the x direction. And I'm going to take that, I'm going to make that thinner also. So these aren't themselves separate forces, but we're going to treat them like they are because the tension has these two effects, upward and horizontally. Okay, back to making our diagram, our equation. We represented, now we're going to create the equation. So in the horizontal direction, we're going to make our net force equation in the horizontal direction. So horizontal. And what that means is let's just put all the forces that are acting horizontally and set them equal to MA. So we have a forward pull from the tension of the rope on the sled, but just the forward amount of that pull. And in the backward direction, we have friction from the ground on the sled. And those are the only two forces acting horizontally. And so we'll set those equal to mass times horizontal acceleration. This part here is the net force. It's the sum or the putting together of all the forces. Some of them are positive and some of them are negative. And then this whole thing here is called the net force equation. All right, let's go ahead and let's use this to try to calculate. Actually, let's also set up the net force in the y direction equation. Again, I want to kind of get everything set up first. So net force in the y direction. All right, and what's that going to look like? Well, in the y direction, we have, let's call up positive. So we have tension, rope on sled, but just in the vertical or y direction. That's that piece right there. And then we have the normal force, ground on sled. That's also directed in the positive direction. And then we have the negative direction, earth pulling down on the sled. And that will be equal to the mass times the acceleration vertically. All right, this again is the net force equation for the y direction. All right, now we really have the problem all set up. We've pictured, we've represented, we've created equations. Now all we want to do is start solving. And so I think I'll use this space in here to solve for number 2. And then I'll go on to another page and rearrange things a little bit, and we'll go back and solve for number 1. So let's flip over to maybe a different color for solving this. The tension in the x direction, that's a given quantity. That's right here. And then the friction, that's a given quantity. That's right here. And then the mass of the sled is given. It's kilograms, so that's mass. And the acceleration is the only unknown, so we can directly use this equation to solve for the acceleration of the sled, which is what we want to do. So putting in our numbers, the horizontal tension from the rope is 60, minus the friction force from the rope is 15. That's going to equal 30 times the acceleration horizontally. And then I'll just do a little math. This is 45 equals 30 a sub x. And so a sub x, which is the horizontal acceleration, will be 0.67. And then we need units, meters per second, which is the units for the acceleration. And so that is how we would use the net force equation to solve for the acceleration. Now, next thing we want to do is solve for the normal force. And so for that one, I'm going to use this equation. And the reason I know that is because the normal force is in that equation. It wasn't in this one, it is in this equation. All right, so now what I'm going to do is clean things up a little bit. I'm going to take all of this and kind of shrink it down. If we need it again, we can always take a look at it, put it over there. And then I'm going to take this, which is of concern of us now, and we're going to use this to solve for the normal force. All right, let's go through and take a look at what we have given in this situation. So the vertical upward pull, that's that one right there, that was given as 25 newtons. Let me not do that. Let me write it like this. Let me just say a little check mark over that. So we know that. The normal force is what we're trying to solve for. The weight is not given. Don't put the 30 up there. That's kilograms. That's mass. That's known. And you may think that the acceleration vertically, the y acceleration, is not known for this sled, but it actually is, because this thing is not accelerating upward or downwards. It's at rest vertically, and it's staying at rest vertically, which means its acceleration is 0. So that's also known. And then what you can see is that we have two variables, which normally would be a problem. But the other day, we did a little pen and paper experiment, or really iPad experiment, where we looked at the relationship between weight and mass. And we found different planets have different lines, but every line has the format y equals mx plus b. And that led us to see that the weight of an object was equal to the slope of this line times the mass, where the y-intercept is 0. And the slope of this was called the gravitational field, and the symbol is the little g for that. And so this thing actually gives us a way to calculate the weight of the sled, knowing the mass that we have. So let's do a little side calculation. Let's do that right now. W, get rid of that. W equals GM. And so G is 9.8, presuming this takes place on Earth, which I presume. And then the mass is 30. And that means the weight, which is the Earth pulling down the sled, will be 29.4. Don't forget our units, newtons. So now let's come up and put some values into our equation. So the rope on the sled, the vertical part of that is 60 newtons. And then the normal force we don't know. So we'll leave that as a variable. And then the weight of the sled is now 294. Sorry, 294. Get rid of that. 294 newtons. And then that should be equal to 30 kilograms times the acceleration vertically is 0. All right. So that means we have only one known, and it's just a question of solving for it. Normal force ground on sled, and that should equal 234 newtons. And that's the answer to the question, what is the normal force on the sled? That is the upward push from the ground on the sled. So at this point, we figured out the normal force on the sled with our net force equation of the vertical, and we found the acceleration of the sled, the horizontal acceleration, with the equation we made for the horizontal net force. We have one last thing to do, which is to calculate the speed of the sled after 3 seconds. Now, if we're being asked to calculate speed, nowhere in our work in forces is there anything about speed. So this is really a motion problem, which means we're going to have to go back to our motion techniques. And so let's see what that looks like. So for our motion problem solving, we would do something like this. We would picture the sled again, going from point A to point B. And then we would represent with a velocity time graph. So starts from rest and speeds up, velocity, time. And then we would write the equation of the line. This is y equals mx plus b form. This is going to be time, let me write this in red, this is time A, and this is time B. And so this is going to be velocity at B equals the slope, which is the acceleration, times the time from A to B, plus the velocity at A, which is the y-intercept. And I think I'm going to change the thickness of those there. All right, the other thing I want to do is, just by habit, is write out the equation of the area. Always picture, represent, and then create equations. So there's the line. And now we want to do the area equation. So the area is 1/2 base times height. But in physics symbols, it's the displacement from A to B is equal to 1/2 the base, which is the time from A to B, multiplied by the height, which is this here, which is the velocity at B, not at A, but at B, velocity at B. All right, and now I want to see, what do I know? What could I use? Which of these could I use, or both maybe, to determine the speed of the sled? So do I know the velocity at A? Yeah, it's 0. I can see from my graph, it says it starts from rest, right here, rest. Do I know the time from A to B? Yeah, 3 seconds. Do I know the acceleration? I do. I calculated that acceleration in the previous slide. It came out to 0.67 meters per second per second. So this equation will get me the velocity at point B, which is how fast the sled is going at 3 seconds. Now let's see if this one would also work. There's our target variable. We definitely know the speed of the time the sled was being pulled by, but we don't know the displacement. We don't know how far the sled was gone in that it went in that 3 seconds. So that's not useful. But this will be. So let's go ahead and solve for that. VB equals 0.67 times 3 plus 0. And if we multiply that out, we should get VB equals approximately 1 meter per second. Again, don't forget the units. Now, clearly, we could take this further, and we could use the area equation, now with the VB known, to solve for how far the sled goes. All right, so going back in review then, force problem solving involves a process exactly similar to everything else we've been doing this year for problem solving. Set up the problem by picturing, representing, and creating equations from your representation, and then solving. In particular, we can build, in this case, we use a free body diagram as the representation. And from that, we build a net force equation, which relies on this relationship between acceleration, net force, and mass. And the net force equation looks like this. Here are the net forces, some to the right, some to the left, equals ma. And we can do the same thing for the vertical forces. And then it's just a matter of going ahead and solving them. So at this point, perhaps your teacher will have assigned you some problems to try using this technique.